Let's continue with the discussion of asymptotic sort of results. So we talked about the delta method. I'm not going to repeat the idea. What I'm just going to do today is tell you about some of the applications. So the first application of these asymptotic results is the so-called relative asymptotic relative efficiency, ARE. The idea is we were trying to compare estimators by their risks, and we ran into issues like in finite samples, things are complicated. One idea is to, like in these settings where we have IID samples, let the sample size go to infinity and then study the asymptotic properties of estimators. Most useful estimators are consistent, so they converge. So let's say I have two estimators that now are going to be parameterized by n, and then as n goes to infinity, they're going to be let's say consistent for some parameter mu of theta, and I have this asymptotic normality result. So these are the things that we try to evolve for M estimators, but in general, you would have something like that. From this statement, if you followed the ideas that we had, if I state something like this, it automatically means that this is consistent for mu theta. So this embedded in it means that this guy is big OP of 1. So basically theta hat IN is, so this implies, for example, implies consistency automatically. So theta hat IN minus mu theta is OP of 1. And so because this is big OP of 1, the difference would be like 1 over root n times big OP of 1, which goes to 0. And then I have this result. So both are consistent for this. The only thing that differs is this asymptotic variance. And now I can say that roughly for large n, the variance of this is of the order of sigma I squared over n. This is not an exact mathematical result. For example, if you have convergence and distribution, it does not mean that the variance of this side is converging to the variance of this, or even the moments. So for moments to converge, you need more conditions. But if you ignore that for a bit, just intuitively what it means is that this is approaching that. So roughly the variance of this, so the rough idea is variance of root n theta hat, let's say IN minus mu theta, is roughly sigma I squared theta. And this is a constant, I can drop it. And then the root n comes in like n times variance of theta hat IN is approximately sigma I squared over theta. And then so the variance of this is roughly sigma I squared theta over n. So that's how these results are like interpreted, as the variance roughly goes down like 1 over n, or the standard deviation like 1 over root n. That's the standard parametric rate. So this is something called root n consistency. So a kind of a statement like this, or a statement like that, basically theta hat IN is mu theta plus big OP of 1 over root n. This is called root n consistency. Roughly what it means is that the variance, let's see, goes down, or the deviations are of the order of 1 over root n, or goes down like 1 over root n, the standard deviation. So if that's the case, roughly what I can do is I can compare these asymptotic variances. And traditionally, the way that people compare this is through this notion of relative efficiency. So you would say that I want to achieve a certain level of variance for my estimator. So I'm going to set these two equal. So let's say if I have a sample size of n1 for the first estimator, in order for this to match the same variance for the other one. So I would need different kind of sample sizes to get the same kind of asymptotic variance. So I'm going to set these equal, and then the ratios of the, let's say, N2 to N1, this is the sample size required by the second guy, this is the sample size required by the first guy. The ratio N2 to N1 is the asymptotic relative efficiency of data hat 1 to data hat 2. And you can see from this equality that this is actually the proportional to the asymptotic variance. Okay, so what this is saying is that if this guy requires more, like N2 is bigger than N1, then the relative efficiency of theta hat 1 is bigger, like better, like this is going to be bigger than 1, so it's more efficient. Theta hat 1 is more efficient relative to theta hat 2. That's why we like divide the sample size like that. And so if the same thing, if the variance, the asymptotic variance. So different people like, or I do different, sometimes call the different things asymptotic variance. Sometimes I call this the asymptotic variance. Sometimes we call this the asymptotic variance. Maybe we should call maybe we should call that the asymptotic variance. So the asymptotic variances are like ordered like this. So asymptotic variance is the second guy divided by the first guy. And so if AR is bigger than 1, then you prefer theta hat 1 to theta hat 2 for that particular parameter. Okay. And again, this could vary as a function of theta. So for some parameters, it could get a bigger, like a bigger than 1. And then for some theta, it would get less than 1. So basically what we're doing is replacing the risk comparisons to like comparing the asymptotic variances, because sort of the bias, asymptotic bias is basically gone. And they're both like consistent for the same thing. You're just going to compare the variances. Sounds good. That's asymptotic relative efficiency. And traditionally, this is a lot of fun to calculate for various estimators because it gives you some sort of a nice measure. So for example, one of the key questions that you can ask is like, for example, is median better than mean? Okay, so that's one question that you can try to answer using that. And this is what people sort of do like in traditional statistics. So suppose I have IID samples from Fx, and this is a general density. I assume that the mean and the medians are the same. So let's say this is, let's say it's a continuous variable. So there's a density, the mean and the median are all the same and equal to theta. Variance is 1. And if I want to estimate the this parameter theta, by CLT, we know that the sample mean, by the law of large number, the sample mean is consistent for this mean or slash median parameter. So that would be, and then we have CLT, so this would be this statement. So we have asymptotic normality, the sample mean for this. And for the median, so this is the sample median. This is sort of the middle order statistic. So when you order things, if you remember the sample median, if I order the observations, so let's say n is yeah, so it's going to be a little bit tricky to define, but let's say 1/2n plus 1, and then so let's say if n is odd, right, it's easy to define. So it would be like I have x1, x2, x3. Let's say I have 3, then this middle guy is going to be the median. If you have 4, then 2 are in the middle, like 2 and 3. So they usually take the average of the 2, or you can do other things. But let's say for simplicity, it doesn't matter as n goes to infinity, whether you look at the one in the middle or like the one below it or the one above it or whatever. So the one in the middle, here I'm going to do like 1/2 n roughly. If you want to be really precise, it should be something like this. But that's the median, and then you can show an asymptotic normality result. So this is going to be consistent for the median slash mean, and you'd have an asymptotic normality result like this, which unfortunately the methods that we have developed are not strong enough to show this from CLT. So you have to resort to other means because this is not a continuous, it's not a continuous mapping or differentiable mapping of some known statistics, so you can apply continuous mapping theorem under the delta method. But Keener goes through this, the calculation for, I think, a simple case, or like basically drives this from first principle. So you can try to calculate the, let's say the CDF, and then show that the CDF converges, I believe. But there are other more like advanced tools that we haven't covered, maybe like in a later potential course, more like technical tools like this book by Van der Waart, Asymptotic Statistics. He goes through tools that allow you to sort of extend some of the calculus that we developed to this, but in any case, so either way, however you get this, this is something that you can show that the median is also asymptotic and normal. And asymptotic variance looks like this, which is the value of the density at theta. Okay, so the value of the density at the this particular median is what controls the asymptotic variance, which is an interesting observation. So nothing else except like the density at this point, because density could like vary very wildly in the tails, but the tails you can imagine doesn't tell you much about the median, because the median is about the center, and this result sort of captures that idea that the asymptotic variance of the median just exactly cares about what happens exactly at the center. And so if there's a lot of mass here, then you would have small asymptotic variance. If you have a distribution that looks like this, maybe symmetric, it's like something like that, right? The median is here, but like the modes are somewhere else. So there's like a little bit of mass here, but not too much, then the asymptotic variance would be high, because you need sort of intuitively more samples to get to the right median. Okay, so these are the two. Then now if you have these, then you can answer whether median is better or mean better for this distribution whose median and mean are the same. So if you look at, for example, the Gaussian family, we have, let's say Gaussian normal, there's a normal location family. It's easy to calculate the density at the mean, which is just going to be the density of standard normal at 0, which is 1/√2 pi. And then for this guy, you can evaluate that this turns out to be right 1/4 times basically √2 pi. So I have to invert that and then square it, so I get basically pi over 2. Right, so that would be asymptotic variance for this sample median. And then for the sample mean, we know that it's just going to be 1, right? Because that's exactly what we have here. So the asymptotic relative efficiency of sample mean, let's say x bar n, relative to the median, let's call it median, is going to be sample median. Is going to be the ratio of the asymptotic variance of the median to the asymptotic variance of the mean. So you're going to need pi over 2, which is 1.75. So roughly what this is saying is that I need like 50% more, or about 60% more samples to achieve the same level of variance as the sample mean if you use median for a normal family. So if you have a normal family, it's better to use the mean to predict that sample mean to predict the mean / median rather than the median, because it's more efficient. Okay. For other distributions, it might be different. Okay. So that gives you some idea why medians haven't replaced means, because medians are robust. So oftentimes in data analysis, you end up with a lot of outliers. So you might imagine that people would use these robust measures. But here's one example of why you don't want to use median, because it's a lot more efficient if you actually have a normal family. Okay, yes.
Does this depend, how does it depend on the variance being one? Could you make up an alternative with that variance where you couldn't median to be? Right?
This would be a great question to actually post, and then you guys answer it. So what do you guys think? Does the variance matter here? So I can, for example, change the variance here, right, to be sigma squared. Does the answer change here? That's great. Yes. So what will happen is like we talked about, I guess, the transformation. So if I have a random variable, let's say I have x minus theta, this is z. To get the variance, I have to like I have now like y, which is sigma z, right? So the transformation of random variables. So the density of this would be, so this transformation would say the density of this would be 1 over sigma, right? F z of y over sigma, right? And so roughly what would happen is that the density, your new density would be, if it used to be, okay, let's not do that. So let's call this actually x. So originally we had the x, now we have y. So x, so now my, so y of 0 would be just not 0, but theta. Yeah, so this is, if you do it on that x, it's gonna mess up the mean as well. But okay, you can figure it out. Okay, so the idea is that you're just gonna rescale this guy by 1 over sigma. So you get something like that here in terms of the original one. Okay, and then sigma squared goes up. So the asymptotic variance is getting multiplied by sigma squared, for the other one is also by sigma squared, so it cancels out. So the answer doesn't change if you change the variance. Any other questions? So it would be interesting to see, for example, you could cook up like distributions whose like this is fixed sort of, but the tails sort of change. And when the tails change, you'd imagine that this might change. But then playing with that, you might be able to find like an example, maybe a heavy tail distribution for which the answer is flipped. Okay. Good. Any other questions? So this is the only example that I'm going to do. You're going to do more in your homework problems. It's just anytime you produce one of these asymptotic normality results or multiple of these, you can compare them. Okay, that's just one of the uses of them. The other use is the confidence intervals that I sort of, I believe, mentioned. So let me ask you guys, what is a confidence interval before we start talking about them, to see if you guys, yes.
It's like the probability that the true estimator with a certain level of confidence will be in that interval.
Yes, so great. So that's exactly what it is. So the probability, so first I like mention that it's a frequentist construction or like a frequentist device. So it's an interval that captures or contains the true parameter with a certain, let's say, probability, or we can say a certain level of confidence. Okay. And so formally, if you want to define it, it could be more than an interval could be a set. So 1 minus alpha level of confidence set for theta naught is a random set. The key here is that it's a random set. Okay. And so it depends on your data, such that the probability that the true parameter belongs to this set. So this true parameter is like unknown, deterministic, belongs to the set S. The probability is bigger than or equal to 1 minus alpha. And we're assuming that we are taking the probability under the true parameter as well. So the randomness is really in this. So what we're saying is that assume that x1 up to xn are coming from this p theta naught. The chance that theta naught under that distribution belongs to this set is bigger than or equal to 1 minus alpha. Then you would say, for example, this is confidence set at level 1 minus alpha. or at least 1 minus alpha. Usually, like if you've done any like real statistics, this is for like the majority of people, this is like 0.05. So this would be 0.95, 95% confidence. I did this, so you say 95%. The key is like this is a frequentist construct. It doesn't mean that what does it mean to have this probability? What does 95% mean? Say it's like this stat, yeah.
Like each time you do experiment, you generate like a interval and 95% of the intervals you generate.
Great. This is exactly what it means. Okay, so this is exactly what if you understand this, like you're like in the 95 percentile of the people who actually understand it. So it doesn't mean that if I like usually you do it one time, the experiment's done one time, you produce this confidence interval. What does that particular interval tell you? Not much. Okay. So what this is saying is that if you now repeat the experiment many times, among these intervals that you generate, 95% will contain the true parameter. For the particular one that you did, you can know anything. So this is like a frequent statistic, and frequent statistics like cares about aggregates, like what happens like when you do things large enough. Okay, so every time you do the experiment, there is a like a interval that you generate. So the randomness comes from the fact that every time you do it, it's going to change. So every time it's going to be a different thing. But 95% of the time, maybe the true parameter is like there. 95% of the time, they capture the true parameter. So this probability that you actually capture the true parameter is called the coverage probability. You set it out to be like this. In reality, it might be something else. So the actual one is called the coverage probability. But if it's like a valid confidence interval, the coverage probability should be. So this is called the coverage probability. It should be bigger than the level that you set. Okay. And there is a trade-off. Once you understand this, you immediately see that there is a trade-off between the size of the confidence set or interval and the coverage probability. I can always like if you're doing a univariate parameter, like estimating univariate parameter, I can always take the entire R to be my confidence interval, and I'm going to be like 100% sure that the parameter is there. But that's not what you want. You want to like find the minimum smallest size such that so basically you want to minimize the size subject to this constraint. And it's very like naturally translate to hypothesis testing. There's a duality, which we're going to talk about. We're going to talk about hypothesis testing next. So there's this tension. Subject to like the coverage probability, you want to reduce the size, and there could be multiple solutions. Okay, so oftentimes we don't try to find the smallest size, but the reasonable size, and try to capture this. So the idea of like usual confidence intervals, so the way to build them is by like traditionally by constructing pivots. Yes.
Sorry, just there's something else for that. You say that confidence intervals aren't necessarily unique for a given confidence.
Yeah, so you could have multiple choices of confidence intervals that give you so imagine so for example you could be like symmetric around like you have an estimate, usually you construct a symmetric confidence interval, but it doesn't have to be, you can shift it around, so capture enough mass.
If you were to change, how would it change the? I guess no, I suppose.
If as long as this satisfied, it's like a valid confidence interval. It doesn't have to be just for example, like people are like comfortable or like used to like symmetric confidence intervals, but it doesn't. I'm going to give you like examples that we can actually build these and they end up being a little bit different. Asymptotically, they're all like, so we'll talk about asymptotic 1 minus alpha. So there are different ways that actually we can construct these. Okay, so usually they're built based on pivots. Pivots are like functions of the statistic, and the parameters, the unknown parameters, such that the distribution of the resulting object does not depend on the parameter. Okay, so it's exactly what I mentioned here. And so here's let's see the classical one. So we have xi from normal, its mean, mu, and variance sigma squared. Z is standardized sample mean, x bar n minus mu divided by sigma over root n. this is the variance of the sample, like the standard deviation of the sample mean. So this is going to be standard normal. And then if I call this Z, because it's standard normal, the probability that it's above, let's say, it's this is like the upper alpha over 2 quanta. So what is the alpha is like where if you have the normal distribution, it's like alpha over 2, so upper quanta. So alpha over 2 of the mass is above this. This is okay. This should be this is not the standard way of writing things, but this is the upper alpha over 2 quanta. So the mass is alpha over 2 above this. And so the probability, so that at some point, the probability that Z is bigger than that is going to be alpha over 2. If that's the case, then it's not hard to see. I'm sure most of you know this. So you in this the absolute value, the probability that this is going to be bigger than or less than this is going to be exactly 1 over alpha. Sorry, 1 minus alpha, because so this is saying I want to be like in this region, and this region contains 1 minus alpha at level like alpha of the mass, because this part is alpha over 2, and this is negative Z alpha over 2. So what this is saying is this guy lies in this interval, and this interval captures 1 minus alpha of the mass. And so if you rearrange this in terms of the mu, in this case, let's say sigma squared is known. I'm assuming sigma squared is known. Mu is our unknown parameter. So if you rearrange it, this just means that mu is going to be in x bar n plus minus sigma over root n times the alpha over 2. And so that would be my confidence interval. So this is random based on the data, and known to me. This is sigma is known, x bar n is going to be known from the data, and mu is unknown, but mu is going to be in this with probability 1 minus alpha. So this is a valid confidence interval. Okay. So what happens if the distribution is not normal? Okay, so we have another one. Let's see, maybe any questions? Yes.
So what is the pivot that they're talking about?
Okay, what is the pivot here? Anyone?
X bar.
X bar is pivot. Is X bar a pivot? Is Z a pivot? So let's hear why this is a pivot or not. Let's hear why this one. So the definition is here. This is a pivot. A function of data, like it could be dependent on data and also the unknown parameters, but whose distribution does not depend on the parameter.
Z.
Z. Okay, Z is a function of both data and the unknown parameter or parameters, and distribution whose distribution does not depend on the parameter. So this is really a pivot. Yes. How about X bar?
It's just a function of data.
Yes, but that's not the critical part. So you could have like only a function of the data, but the key is the other as
Distribution depends on the parameter that we want to be.
yeah. What is the distribution of this guy?
The normal distribution is made of mu and then
Mu, right? Right. So the mu here is the problematic. So the distribution depends on mu, and so I can't use it to construct confidence interval because I don't know the parameter. So the rationale behind like defining a pivot is that once the distribution does not depend on the parameter, I can use that distribution to set the interval. Okay.
But
Then-
you want your pivots to be sufficient statistics? So, or you don't say it like that.
So they're usually not statistics at all because they depend on the actual
Oh, yeah.
unknown parameter. But oftentimes, like the part that depends on data is usually dependent on data through the sufficient statistics. But that part is like all the things that you know. Like so far, you want to incorporate into constructing it because otherwise it's not going to be that informative. So basically, oftentimes, so they're built on based on like already known point estimate. So this is something called the point estimate. So X bar n is a point estimator for mu, and you manipulate it a little bit to get something whose distribution does not depend on the parameter, and then based on that, you construct it. Yes.
But so X bar is still like a part of the confidence interval, so the confidence interval doesn't have to have only pivots in it.
No, like in the end, what happens is that the confidence interval just has to depend on the data. It can't depend on the unknown parameters, otherwise it's not a useful confidence interval. So here is like sigma, let's say put it to equal to 1. This I know, okay? So this is something that only depends on the data. So as you can see by definition, this set has to be a function of the data. So it's really a statistic.
Okay.
It can be computed from the data. So in the end, if you end up with something that has the unknown parameter in it, then you're not producing confidence interval, right? You want an interval that you can compute from the data. Okay, but you manipulate the expression in terms of the pivot, something like that. So this is like saying basically z, the probability that z is bigger, like less than or equal to z over alpha over 2 is 1 minus alpha. That's like that I can do, but you manipulate this expression to write it in terms of the unknown parameter. The probability that unknown parameter belongs to Ci is, let's say, 1 minus alpha, and this Ci only depends on the data. Does that make sense? Yes.
You said that if, like, a confidence interval means if you repeat the experiment several times, 1 minus alpha % of the times.
Yes.
It captures truth, right? But in papers, we read only one confidence interval, and what am I supposed to understand from that?
So can you like repeat the last part? So in papers, you have like one confidence interval, right? Is
Yeah,
that
when they report something, they just give me one interval,
yes?
and what should I understand from that interval?
You guys tell me. What should you answer? Yes.
If they give you a confidence interval, you should just know that, you don't want to look at that and say, oh, well, the true parameter lies in that 95% of the time. That's not what you want to say. You want to say that if I was to redo this experiment like 100 more times, 95% of the intervals generated would contain the true parameters. So like,
That's exactly the true thing. So you can't say, for example, that interval contains the true parameter with 95%. That doesn't make any sense. So that interval may or may not contain the true parameter. We can't say anything about that. That's the beauty of like frequent statistic, is that I can't tell you anything about that particular one. Okay. I can tell you what happens if many people like try to replicate it. And if they try to replicate using the same procedure, the thing is that they have to produce the procedure. If they try to replicate it and you see like maybe like 50% of the time it contains it, if 50% is not, then the procedure that the estimator, like, or the confidence interval, which you can think of it as a generalized estimator, is not a valid confidence interval, that we can say. Or if we can see like 98% of the time it captures, then it's a valid confidence interval. That's what it means. Okay. Is that not good enough for you?
Although, like, I don't understand what's the point in reporting confidence intervals. They give some results.
What is the point? Because it tells you something about like the uncertainty that captures. So if I just give you, so I'm going to do this experiment, and I tell you that mu is like 0.1. Okay, it doesn't tell you how confident I am. Like the confidence part comes a little bit from the uncertainty part. So you can see like when you build this, usually there is some sort of a measure of the variance of the estimator that goes into the length. So the length of it tells you something about the size of the variance of your estimator, right? The sampling variance of your estimator. So if it's wide, then you expect that probably you don't have enough samples, or like this is like not very certain. If it's smaller, then, but the wrong way of interpreting is that the true parameter is there with some sort of level of something. Okay, that I can't tell, but you can think of the way you usually think about it is, and it's helpful, is a way to normalize things. Okay, so it's a way of normalization of your statistic. So people sort of can report can I tell you? So the p-value is basically a little bit better to understand. Maybe I'll discuss this when if we get to p-values, then or if in a different life we'll get to p-values and I'll talk about that. But it's a way of normalization. Okay, so if everyone is doing that, let's say if like in science, they're following a procedure and everyone reports the same sort of thing, right? Then you can go aggregate across multiple studies and see like you can get some information, right? That's what I say, but the advantage basically from just one study is that it tells you something about how confident or like how uncertain the estimator is. Like something
That would
about,
again depend on the variance, right? Like if I say my estimate is 1 and my confidence interval is 0.5 to 1.5.
your estimator is 1, like me, it's like a sample mean is 1, and you're like sigma over root n. That's the variance. So this is what, like, let's say point. Okay, it depends also on this.
Exactly.
But yeah, so if this is what? 0.5, right? Is that, so what then? What's the conclusion? Sorry? So let's say if it's like this versus if it's like that, it gives you some information, right? For example, if it's like this, it tells you that they had more samples, let's say, assuming that the variance is fixed. So let's say you're doing like the sample mean in a Bernoulli trial. So let's say x1 up to xn are Bernoulli with parameter p, you're trying to estimate p, right? So you know that the variance of this guy is what? Right, this is at most, what? Sorry? At most 1/4, right? So you know that like if I give you sample mean, plus minus, so this is not exactly normal, but our asymptotic version would cover this, plus minus, let's say, if I increase the like variance, I'm gonna do better, right? So the worst case would be like, I'm gonna bound by 1/2, which is sigma and the root n. And this is, anyone knows, like if I have 95%, what would be this sort of, like this is gonna be 0.05, so alpha over 2 would be 0.025. So this for a Gaussian would be like 1.96 or something, right? So that would be your confidence interval, right? So if someone tells you, or you could do, we'll see, you could do like x bar n plus minus x bar, and this is an estimate, right? I can do something like that if you really want to like nail it. As we'll see, both of these so this is going to be like asymptotic CI, as we'll see. At level exactly that, this is going to be at level slightly probably better. But in any case, if I give you, for example, this, based on the length of the interval, you can tell something about the sample size that they have. So it tells you if you don't report your the sample size, but if to follow the procedure correctly, you know that the length is roughly going to be like, you can invert it, right? And that tells you something about the uncertainty, right? Sounds good. Good. Okay, people are really interested in confidence interval, it seems here. Okay, any other questions? So the other example, for example, again, a very classical example is that if I have x1s up to xn's are normal between mu and variance sigma squared, the sigma squared is now unknown. Okay, this is still a pivot. But if I do this procedure that I did here, this is not going to be a valid confidence interval because if sigma squared is unknown, I don't have sigma, so I can't report that as a confidence interval. What people do is that they look at Z divided by this. And so if you look at this, Sn squared was the sample. Yeah, this is the sample variance.
So I guess why is it divided by n minus one instead of n? Because n minus one is like supposed to be not exactly the sample variance.
So anyone wants to tell me why it's, sorry? Yes, you said unbiased. You want to say
It's like the degrees of freedom.
degrees of freedom. Yeah, so it has a lot of interesting properties. So this is going to be unbiased, whereas the other one is not going to be unbiased. And also, if you look at this and then look at this guy, this is going to be. So if you ignore it, so multiply this by that. So this guy is going to have a chi-squared with n minus 1 degrees of freedom. Okay. The reason being, so x bar depends on xi's, but you can write this in terms of a projection if you want to like write it. Like if x is the vector, it's going to be x transpose a projection matrix, which is I minus the rank 1 projection, and this would have like because of the projection would be like anyone knows what the projection matrix would be here? So 1 transpose over n. If I'm not wrong, then if you take the projection to be this, then this is going to be like chi-squared to the rank of the projection, something like that. Yeah, this has to be like standard normal. So if Z is standard normal, standard normal vector, then Z transpose P. Z in general, if it's a projection matrix, it's going to be chi-squared to the rank of the projection matrix. This you can show. If it was a different course, I would show this. Yeah, roughly speaking, this would be equivalent to PZ squared because projections are idempotent, and PZ you can do like eigenvalue decomposition. So you can argue for yourself that this is going to be the case. And in this case, the rank of this projection matrix. So this projection matrix basically subtracts. So if I multiply it by a vector, you can see it just P times Z would be like Z minus the 1 vector and then 1 transpose Z over n. So it takes the average and subtracts it from a recording. Okay, this projection is sort of P means or like. So because of this fact, this is the rank n minus 1. So the rank of this is n minus 1. That's why you get a chi-squared in what like 1 degree is removed. Okay, because this basically you're projecting onto a smaller thing. This is a very short footnote. If you're interested, you can follow up on this. But that's another reason. Okay, so this is chi-squared with n minus 1 degrees of freedom. Now, if I divide this by the degrees of freedom, okay, so if you have a chi-squared, and it turns out that this is going to also be independent of the sample mean that we have shown, like by Pesso's theorem, or you already know. So this divided by so in our case, this has to be divided by sigma squared because this is not a standard normal. So I have to divide it by sigma squared to make it essentially based on standard normal. But this is going to be chi-squared, and then now if I define this to be V, and if I have a chi-squared distribution divided by its degrees of freedom, something like that, take the square root, put it in the denominator, and then another standard normal on top, independent of this, then this would have a t-distribution. That's the definition of t-distribution. So that's basically why people work with this. And now this is really a pivot. This was also a pivot, but this is a pivot, and it's good because the only thing that depends on, so this guy, you can see when I divide these, the sigma cancel out because there's a square root here, sigma cancel out. And so sigma goes away, and I only have mu there. And so because it's a t-distribution, I know what, for example, let's say the quantiles of PR, And I'll have this probabilistic statement, and then I rearrange it, like, I'll take a result like that. And so now I have this as n here instead of sigma, but this is now going to be t quantile, and this would be an exact 1 minus alpha confidence interval. Okay, so these are the technologies that like very classical, goes back to a student's paper, 1920 or something. Yes.
Yeah, I guess for the students, teams always seem to me to be kind of like a clunky level of variance, or it just seems like it causes like a lot of issues. Like, would we do it the same way if we had the chance to like go back and look at it, or the other ways to handle variance?
Why do you think it's clunky?
It's like having to deal with like introducing the customer distribution. And whatnot, or like having how to rise this when it's going to go away. Anyways.
The thing is, this is a good estimate of the variance, right? This is not, so if you look at the end result, this is the sample mean, this is like a natural estimate of the variance. The only question is that what should I put here to make sure that this captures the mass? And this calculation just tells you that if you put like a tails of t distribution there, it's going to work. Okay, it's the confidence interval construction, the length is good. Okay, what we'll see is that this is like asymptotic is going to be like a normal. So you can put a normal quantile here. Asymptotically would work fine, right? That's basically the main like point, is that you don't have to do the exact calculations if your sample size is large enough. So people do this because like if things are normal, this is going to be exact for any n. Okay, but if your sample size is very big, you don't need normality. You can appeal to CLP, and at that point, everything is going to be normal. We'll see. Any other questions? Yes.
So the asymptotic part is why 400 years ago, when I took my first stats class, they said you have to use the t distribution if it's like
400 years ago?
that's how long
You're very old.
Yeah.
Okay. So what did they say?
I was saying that like the first stats class I ever took, they talked about, oh, use the t distribution if it's like less than 20 sample size or whatever.
Something like that. Yes, but then you have to believe that this is actually true, which you may or may not believe.
Right.
Yes. If you believe that you're like exactly from normal distribution, which is like I think more serious assumption, then yes, I mean this is going to be all exact. You can use t if you're like below that part. I don't know, which like below whatever. Like that's like a rule of thumb, but that's where the CLT kicks in, sort of. You already like should understand what happens. So asymptotically, this is going to converge to the variance. Asymptotically, this looks like 0 over like a fixed variance. Asymptotically, it looks like a normal distribution. So actually, sorry, this is going to converge to 1 actually because of the way we normalize. Okay, any other questions? So what are asymptotic confidence intervals? Asymptotic 1 minus alpha confidence set or interval for theta is just exactly that, but the other side doesn't have to be exactly 1 minus alpha, but just has to converge to 1 minus alpha as n goes to infinity. So the coverage probability converges to 1 minus alpha as n goes to infinity. And these asymptotic results give you a natural way to construct such asymptotic confidence intervals. So you have, for example, root n tn minus theta naught converging to a normal between 0 and variance sigma squared theta naught. And so if you look at what I wrote there, so Tn basically plus minus sigma squared. Now evaluate the Tn because Tn is going to be consistent. So Tn is going to be theta naught plus little OPO or big OPO 1 over root n, if you remember. So Tn is a consistent estimator of the variance. I would say, for example, something like, I would like to write something like that, but I don't have theta naught, so I just replace theta naught with Tn, which is an estimator. And this thing is going to be a valid asymptotic confidence interval at level minus alpha. The way to prove it is to basically appeal to some of the results that we know. So Tn conversion probably to theta naught. Actually, we know more to convergence at this rate. And then by continuous mapping theorem, so now I'm assuming that sigma is continuous, so that's part of the assumption. Sigma theta naught divided by sigma Tn converges in probably to 1. Right, that's continuous mapping theorem. And then if I look at something like this, I'm basically dividing this guy by sort of an estimate of the variance. Look at this, if I multiply it by sigma squared over root sigma squared over, sorry, root sigma squared at theta naught, and then divide by the same thing. So I'm just multiplying and dividing by this quantity. You'd recognize that this is the original statistic, basically. So if I have this statement, I can divide both sides by sigma squared or value of theta or theta naught, because that's a constant. So this is going to converge by a Slutsky or continuous mapping theorem to 1. So this is, I'm doing this on the fly, basically. This is an easy result. This follows if I do that. And so this converges in distribution to normal 0 or 1. This converges in probability to 1. Okay. Can I conclude that this result, the product conversion distribution to normal 0, 1? Why?
As like a constant in terms of the distribution, well,
Right. Does it have a name, the result that we're using? Slutsky, yes. Just one word solves everything. So Slutsky. So you can just appeal to this theorem and just solve all your problems if you're doing it right. Which is in this case, one converts distribution to a random variable or a genuine distribution. The other one converges in probability distribution to a constant, so the product converges. Okay, so we have shown that this is an asymptotic pivot, right? Distribution asymptotically does not depend on the parameter, so I can treat that. I can write some probabilities. For example, I can write we call this Zn. I can say the probability that Zn is bigger than or equal to, let's say 1.96 is going to be converging to, because this is going to be a normal, it's going to be converging to what? 2.05. Or in other words, if I write something like Zn less than or equal to this is going to converge to 95%, 0.95. This is from the conversion distribution. Because the distribution, this is conversion normal, the probability of this, basically any interval should converge to the probability of a, if you want to be precise, the probability that Z, the generic normal, is less than 1.95. So this is going to be, sorry, 1.96 to the 0.95. And so if I like rearrange things here, I would get the interval. So I encourage you to just rearrange this statement. This is saying this guy is an absolute value less than or equal to 1.96. You rearrange, write it in terms of theta naught. So it's saying the probability that we see theta naught is in Tn plus minus root sigma squared Tn over n times, let's say 1.96. This is going to converge to 0.95. So this is a valid confidence interval, asymptotic confidence interval. Yes.
And the sigma squared of Tn, that's just the variance of the statistic T.
That's your estimate of the asymptotic variance of the statistic, because this is the asymptotic variance. This is not necessarily the variance of this, right? But the asymptotic variance. Yeah. And all I need is the asymptotic variance to get these asymptotic. Okay.
Well, with the sigma squared theta and the sigma squared Tn are they're
Different.
right, different. Okay.
But one is the estimate of the other. So that's this part. So this guy is a consistent estimator of this.
Yeah.
Okay. If I replace this with theta naught, this is not going to be useful because I don't know theta naught. Right? But like a bit of like Slutsky and CLT tells you that I can just replace it with Tn, and asymptotically nothing changes. Okay. So that gives you a general recipe for constructing confidence intervals. Questions? So you can build, for example, confidence intervals for the median. If you believe that asymptotic normality result that we had, so this would be like 1/4 the square of the density at the median. And no questions? So a bit about the MLE. Let's see how much I have. So the MLE, for the MLE, we can use the same procedure. So for the MLE under the regularity assumption, so if theta hat n is the MLE of some parameter, we know that it has this we have this nice asymptotic normality results. The asymptotic variance is going to be 1 over the Fisher information. So I'm not going to repeat it. This is exactly the same procedure we did. So if you reapply this result, right? So if I apply this result with the MLE, what I would get is, for MLE, sigma squared theta naught would be just 1 over I theta naught. So what I would get is theta hat n plus minus, I would get, goes like in the denominator 1 I theta hat n, and then root, and then z alpha over 2. Okay, so that's how it looks like exactly like what I wrote here. That's one way of constructing an asymptotic confidence interval for the MLE. There are other ways as well. So this is clear, just in a special case. The other way is look at the log likelihood, which is just the sum of the log likelihoods of individual samples. And we know that the Fisher information is something like, this is missing, so L n theta, so the second derivative multiplied by a negative sign. The expectation of this, that's the Fisher information. So in other words, this is expectation of negative L double dot and theta, right? Or expectation of actually one of them. Sorry, this is not what I mean. This is for a single one. So expectation negative log p theta of one of them. Okay, so this is Fisher information based on a single sample. And because this is an average, so L double dot and theta would be like, if I divide by 1 over n and put a negative sign, it's going to be 1 over n summation I from 1 to n negative partial second derivative, basically log p theta of xi. So by the law of large numbers, this converges to, in probability converges to the Fisher information. Okay, so this guy is a consistent estimate of the Fisher information. Sometimes it's called like the sample Fisher information, right? An estimate of the Fisher information. And so this is true. Sorry, this is true for a fixed theta. If we assume the Fisher information is so unbiased, consistent, if we assume that this guy is continuous, let's say, assume that L double dot n, assume this is continuous, continuously differentiable, basically model, continuous. I can replace theta with theta hat n, and I still would converge to I theta naught. Oh, actually, no, sorry. This is not correct. Yeah. So this we need a little more. So this holds for any fixed theta, right? I want to replace the theta with theta hat n, which is now like a moving target, which also depends on L double dot n, using the same sort of arguments for the asymptotic normality of the MLE, like the equicontinuity, if you remember, stochastic equicontinuity. If those conditions hold, this is going to be true. So evaluating this at this point, which is converting to theta naught, is going to also converge to I theta. Okay, so I can wave my hands a little bit and argue that this is consistent as well. So this is really what is going to be helpful, because this is like a sample version of the Fisher information. I can estimate the Fisher information from data, and so I can reword this statement. by a little bit of Slutsky or continuous mapping theorem like this. So this divided by, if I divide both sides by 1 over, so I divide by I theta naught, take the square root, it still holds, something like that. And then I multiply by this result. So this is, so we know that theta hat n minus theta converges in distribution to normal with mean 0 variance this. So I divide, sorry, this is multiply. So this is 1 over I theta naught. I multiply by this guy. This is the easy thing to do. So this converges to normal 0 and 1. So this just renormalizes this Fisher information is constant. So I have this. Now I multiply both sides of this by this quantity. Not both sides, sorry. Multiply and divide. So no, sorry, multiply. Just multiply by this. Multiply this by that, because if this converges in probability to 1, this converges to normal 0, 1. The result by Slutsky converges to normal 0, 1. And then you can see these two cancel out. These two cancel out, and I get that this converges to normal 0, 1. So I can just replace that n, this guy that I had, or n I theta naught by this basically negative L double dot theta hat. So this gives you a different asymptotic confidence interval, but asymptotically it's a valid confidence interval, assuming that what I mentioned here is true. Okay, I just did this to give you an idea that there are various versions. So asymptotically, they're all the same, but for finite sample, they might behave different. Yeah, so I'm gonna skip like discussing more, but there are other variants, I believe, as well. So you can look at the book. Questions? Okay, so let's try to recap, not recap, but just finish this, hopefully. See if you can actually talk about a little bit about hypothesis testing. So the last thing that I want to talk about, so we saw that asymptotic normality is useful for comparing estimators via asymptotic relative efficiency. Is useful for building confidence intervals, asymptotically valid confidence intervals. This is the last one, which is related to basically confidence intervals as well. So you can use it to construct these variance stabilizing transforms. So you can construct things, transformations of your statistics such that the asymptotic variance does not depend on the parameter. Okay, so let's do this. So I have this asymptotic normality result, and by the delta method, if I apply a function here, f to my statistic, ftn minus f theta root n convergent distribution to they're like the same thing, but the variance is inflated or multiplied by this factor. So how can I like make the variance constant? I can sort of basically set this equal to a constant and solve for f. Okay. And if you do that, you get a nice result that you have an estimator whose variance does not depend on the actual parameter. It's sort of like a minimax kind of thing, but like not minimax, but equalizer. Remember, equalizer, the risk does not depend on theta. This is like the asymptotic version of it. So here's an example. So this is good for building asymptotic pivots because once this side like is constant, then I have a pivot, right? Because the distribution no longer depends on the unknown parameters. So for example, if you have Poisson, mean equal variance is equal to the variance is equal to theta. So the CLT would look like this. Mean is theta, variance is also theta, so it looks like that. So if I want to solve that equation, I would have like f prime theta times the variance, which is theta. I want it to be equal to c. Let's say I'll set it equal to 1. So I get that if this has to be plus minus, but I can take it to be like this, for example. And one function that does this is 2 theta. Okay. So if I do that, if I multiply by not multiply, but apply this function to the result. So I'm going to apply this to this and to this. So I get that this result. Okay. Apply f to both. And now this is an asymptotic pivot because the other side does not depend on the unknown parameters. So this has to be, so if I set this to be in minus 1.96 and 1.96, I would have like a 95% asymptotic confidence interval. So that would get you this. Okay, so you'd see that. But I mean, a different procedure that we follow, like earlier, I can just this procedure. This one gives you a different confidence interval. So this, if you do that, it would give you this confidence interval. And it's a very fun exercise for you to try to figure out. You do like write some R code and try to figure out which one is better or like under what circumstance. So there are these two confidence intervals. One depends on so you can see that by doing this, the center also changes. So you change the center and the length for the scale. Here, the center is something else, but the scale is different. So they're both asymptotically valid, but they look different. Okay. I'll leave it to you to decide. Is there any advantage to one of these? Good. So variance stabilizing transforms can be used to construct asymptotic pivots, which can then be used to construct asymptotic confidence intervals. Okay, these are some of the uses of asymptotic normality results. Classically, perhaps the most useful is like building confidence intervals and characterizing uncertainty. Good. Any questions? So with that, we conclude the discussion of asymptotics. This is the last topic that I want to talk about. Let's introduce. So hopefully most people know about hypothesis testing, right? And this, in a sense, is a simpler sort of version of the decision theoretic problem that we started with. So if you recall decision theory, we had a probabilistic model, a parametric family of distributions parameterized by some parameter or an observation X in some sample space. In the most basic form, hypothesis testing is the case where the parameter is just binary 0, 1. A little bit more advanced version is where you partition there's like a real valued or like multivariate parameter, but you partition the space into two disjoint sets, and you only care about figuring out in what part of the space the parameter comes from. So I have a real valued parameter. I don't care about the exact value of it. I just care about whether it comes from this part of the space or the other part. Okay, so for example, if you have a fair coin, you might not fair coin, but you have this Bernoulli problem, right? X1 up to Xn. So you might want to test whether this is equal to this or this is not equal to 1/2. So being fair is like a critical thing. So theta is either 1/2 or not 1/2. So one of these sets is a single point, the other is everything else. Or you could say, for example, if this is bigger than 1/2 versus less than 1/2 or something like that. So this more general setting is sometimes called composite hypothesis testing. The other one is simple hypothesis testing. So that's the decision problem. We want to decide which piece it belongs to. So a natural thing to do is for this more general version is to estimate the parameter. And then my decision rule will be something like this. Declare. So I'm going to declare the index here. So 1 means I'm here, 0 means I'm here. So this indicator is something like that. So if theta hat belongs to omega 1, I'm going to declare 1. So 1 occurred, which is called alternative usually. And in the other case, 0 occurred. Okay, or you can say these are complement of each other, so they partition the space. But there's this general principle in the statistic that sort of this is like informal. Do not estimate more than what you care about. Okay, so if you only care about this division, you don't have to like precisely estimate theta hat. Because if you try to estimate theta hat, then you would spend your data budget on something that you don't care about. So this is going to be less efficient. It's good. It's like plug and estimate, like an example of plug and estimator. But you could probably do better if you only care about that dichotomy. Okay. So the other part is the more complex your model is, the more potential to fit to noise. So if this is really, for example, very complicated function, if you try to estimate it with all its details, you're going to pay a big price. Whereas if you are trying to say whether it's 0 or not, it's a much easier problem. Okay, we're out of time, but let me maybe mention that. So we're going to set this problem up in terms of this classical framework. You have a null hypothesis, which says that theta is in omega naught. You have an alternative, which says theta is in omega 1. And then a test would look like this. So when x is in S, I'll declare 1. Otherwise, I don't. And then there's going to be a trade-off at a time. So I'm going to come back and talk about this. So there's a significance level and a power of the test, and these are in tension. So if I come up with a decision rule like that, these are the general decision rules that you can consider. I just have to specify that critical region, that's where x lands, and I declare the alternative, or let's say reject the null. And the power is the probability that I do this under the actual alternative. The significance is the probability that I do this under the null, which I shouldn't. So and then the thing is that we have to balance these two conditions. And then this leads to the name of Pearson framework on how to maximize power given a fixed significance level. So next time I'm going to come back and talk about these.